Hi guys, today's video is a follow-up of my previous video that I showed you a few scary PCB mountable high voltage and quite high capacity capacitors. Sounds good, high capacity capacitors. Anyway, in this video I mentioned I want to show you the ESR, just to show you, not make a dissertation about ESR and explain the theory. There are a lot of videos on YouTube and a myriad of informations on in the internet. No need to invent the wheel again. So I want to show you some capacitors that I had in my previous video, some new ones, in particular one new one. And I thought, while we are doing that, I will show you a comparison between some electrolytic low ESR capacitors that are a near equivalent to some of those non-polarized that I showed you. Yeah, just for the beginning, and this will be the only theory for today, nothing else. What are we speaking about? We are speaking about the capacitors and the ESR. So, my beautiful drawing here, this is how a capacitor should look in an ideal world. But we all know that we are not living in an ideal world. In the electronics and in general, our world is not ideal. So instead of a capacitor looking like that and behaving like that, like a pure capacitor, it looks like that with parasitics. So you have a resistor in series, and a coil in series, the windings of the capacitor, the everything, and then you have the capacitor itself. In reality, you would have, in parallel to the capacitor, one other resistor, but okay, this is not interesting for us now. These are the three main components of a capacitor. And the resistor represents the ESR, the inductance, the ESL, equivalent series resistance, and equivalent series inductance, and the capacitor itself. So, and today we are going to measure this thing, nothing else. So, that was the whole theory. Everything else, it's widely available in the internet. I will put some links in the description if you want to know more about ESR, ESL, and these things. But for today, the purpose of this video is to show you how these capacitors that I have here, these ones, I have to zoom a little bit, but it is not that easy with the iPhone. Yeah, these capacitors, how they look in means of ESR. So let's start. And to check the ESR of the caps, what I want to show you, I'm using my trusty LCR meter, the DE 5000. This is how it looks. It's accurate enough for everything that I want to show you today. And it has a resolution down to 1 milliohm in the resistance range. More than enough for everything that we need. And frequency range between 100 Hertz and 100 kilohertz in steps. So for the first capacitor, I have three capacitors that I do not have data sheets because I don't use them. I have data sheets, but makes no sense to show it. It is a low, this one for example, a low capacity capacitor, how that sounds, huh? It's a 12 microfarad at 1300 volts. For that, I will show you only the actual ESR, and not too much with doing with data sheets. But there are other ones that are compared with the data sheets and with electrolytics. But for the beginning, 3 capacitors, non-polarized, just to give you an example what we have to expect in means of ESR. So let's see what we're going to do now. We will connect this thing. This is quite. Connect one here and one here. And let's see what we have in means of ESR. Of course, we're at 10 kilohertz. So we are at 10 kilohertz at the moment, and the ESR reading here is too low to be shown. And if I go to the 100 kilohertz, even worse. Just for information, this is the capacity at 100 hertz, and let's go to 10 kilohertz again, because this is the normal frequency these capacitors will be tested. You see, it is under 10 milliohms. Yeah, that means we have to leave this setting and go to the resistance setting. And we have 9 milliohms. And if I go up the frequency of 100 kilohertz, look how it falls. 2 milliohms, guys. 2 milliohms. Never, never, ever you will get that with an electrolytic capacitor. And I show you how the electrolytics behave after that. But let's go again at the capacity settings. It is a little bit cumbersome to do that, but okay. Anyway, this doesn't stay where I wanted to put it. 1255 microfarads at 100 kilohertz. And here I want to show you too that how the frequency influences the capacitance. 100 hertz, 11.78 microfarads. Let's go to 10 kilohertz. 1178 something. And at 100 kilohertz, it's already 1253. So here you see the influence of frequency to the capacitance, to the ESR, to everything. Yeah. Let's go back to 10 kilohertz and let's go again. This is really cumbersome, but okay, I have to press 1 million buttons for that. Yeah. Okay, let's take the next capacitor. The next capacitor is a opala, upside down. David Jones would say the electrons will fall out. Anyway, here it is. It's a 30 microfarad, 900 volts. Low ESR, of course, again. Somewhere I had my screwdriver to discharge the capacitor. Yeah, just to be sure. And let's connect it. Again, this is just as a comparison thing, nothing else, yeah? Here we have at 10 kilohertz. It's a little bit difficult. Here you have it. It wants the D. I don't want D, I want ESR. And again, the ESR at 10 kilohertz is too low to be displayed in a 3-digit value. So let's go back again to the resistance. We have 7 milliohms. And if I up the frequency to 100 kilohertz, 5 milliohms. Why this thing is flickering? Yeah, I don't know. It's the light. Yeah. Is that better? No, like that. Yeah, let's leave it like that, probably. Yeah, so this is the 30 microfarad one. And now I have one I have a capacitor that I didn't show you before. This one. Oops, again, everything is upside down. You see? I see it better here. This one is a Cornell Dubilier, or the Doublier. I don't know how to pronounce it. It's a 3 microfarad, 1200 volts. It looks not really big, but look, compared to my hand, it is a biggie, yeah? That's the 30 microfarad 900 volt, and that's a 3 microfarad 1200 volts. So, let's connect. Again, discharge it. And what we see here. Let's go again to the, sorry guys, ESR. Let's go again to, this is the only cumbersome thing of this instrument. I hate it, that it doesn't stay where it should be. Anyway, let's go to a frequency of 10 kilohertz again. And again, it goes away from DSR to dissipation mode. Here, instead of showing ESR, the GUI is crappy, but anyway. 10 milliohms at 10 kilohertz and a capacity of 2.9 something microfarads. And if I up the frequency to 100 kilohertz, it goes, the ESR goes a little bit higher, interesting, and the capacitance goes higher. Let's go again to see it a little bit more. And again, the wrong button. 31 milliohms for this capacitor. Three microfarads. You can imagine what the ESR is of a 3 microfarad electrolytic capacitor in the ohms. Yeah. So these are the 3 ones I wanted to show you just for fun, for the beginning. And this one I didn't show you at all. Using that for resonant capacitance for ZVS circuits, high power ZVS circuits. But now, let's put this away. I want to show you the first capacitor where I will show you an equivalent, an electrolytic, and more or less equivalent, an electrolytic capacitor. So the first capacitor that I've chosen is this VIMA, 22 microfarads, 900 volts. Here's the data sheet. And let's go down, zoom a little bit down, down. Interesting is that this 22 microfarads is not in the data sheet. So I think it is quite an old model that is not produced anymore. But anyway, we have a 20 microfarads here and the 25 one. So the nearest one is the 25 microfarads, and it should be at at 10 kilohertz, the ESR should be something near 4.8 milliohms. Let's see if that's true. And again, I hope you believe me that I'm connecting it. So 10 kilohertz again. Forgot to discharge it, because if I don't discharge it, it shows a little bit too high ESR. Interesting. So let's try again. Should be something 4.8. It's a little bit more. It should be in the way of 3 something. Anyway, it says 0, it says 8 milliohms. Let's use another contacts. Normally, you should use all 4 contacts. Now I'm using only 2. It's interesting that now, when I tested it before, it showed me 3 milliohms or something. And now, I don't know why. Okay, let's discharge it again. Let's go that way and that way. Yeah, okay, something 7 milliohms. And if I go to up the frequency at 100 kilohertz, now we have 3. What was the frequency? 10 kilohertz. Anyway, you see how low the ESR is. But now for comparison, we have 22 microfarads, 900 volts. So I do not have an electrolytic capacitor that is 22 microfarads at 900 volts. But the nearest thing that I have is this one. It's an Aishi, low ESR, 47 microfarads, 450 volts. That means I have to take 2 of them in series to reach the 900 volts and to have the capacitance to more or less 23 something microfarads, near enough to that. So let's take a look of the data sheet. This is the Aishi datasheet. High frequency, low impedance, blah, 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 blah. It doesn't specify the impedance at 10 kilohertz, but we will check it now. By the way, I have many of these. If you're interested to buy quality products from Asia, from China, and of course, these things I would never buy it on AliExpress or on eBay. There is a company called lcsc.com. It's a distributor, a trusted distributor for quite many years that I buy from them too. They have first of all, they have brands that you will never find here in Europe, like this Aishi. Never saw that before, yeah. You can find a lot of chips that are made for the Asian market, that will not be faked, and cheaper. So, just for information, yeah. I like to use Asian chips because they are made specifically for the Asian market and specifically for a specific job. You know, you don't take a Texas Instruments that, okay, I can take it, I have to make a few changes, a few compromises, etc., and it will work. No, I find chips there, for example, charger chips that do exactly what they want with an absolute minimum count of external components, because every external component costs cents, and everything that is built there is built to an absolutely low cost. So, but I will make a different video for that, just to show you how I'm choosing components from Asia. Anyway, many. So, but we are at the, yeah, so let's take this one, low ESR, guys, yeah? 47 microfarads, 450 volts. Minus. Okay, let's go down to 10 kilohertz, because otherwise it will say, it will puke. You see that? At 10 kilohertz. It's 1 ohm, 1.5 ohm. Yeah, let's bring it a little bit near. At 100 kilohertz, it's a little bit lower, but still in ohm. And let's check the capacitance. Oh, sorry. Here we are. At 100 hertz, it's 43 microfarads. Look what happens if I go up with the frequency. 43, 42, 100 hertz, 1 kilohertz, 41, we have 35 microfarads, and 100 kilohertz, it goes berserk. This capacitor is not meant to be used at these frequencies. You see what the capacitance is going. And you have the same situation with multi-layer ceramic capacitors that are frequency dependent and voltage dependent, even worse. Yeah, this will be another video. Anyway, so, but this, let's back up the frequency a little bit. The highest frequency that is more or less usable, 10 kilohertz. No, 10 kilohertz. Yeah, anyway, 10 kilohertz. We have already 1.46 ohm resistance. Now, to get the 22 microfarads to 950 volts, you have to put 2 of them in series. That means you will get up to 3 ohms of ESR. And you don't believe me? Wait. I have the feeling that this video is going a little bit too long again. So, look what I did. 2 capacitors. And I'm connecting them in series. Just for you to see. But let's check the display here. Cannot put everything in one place. So, 3 ohms. That's Ohm's law. Resistance in series. It doubles the resistance. That means this is the big difference between 2 of these and this one. 900 volts in series, 23 microfarads, 22 microfarads. 7 to 8 milliohms ESR, 3 ohm ESR. Wow. So, let's continue. Oh boy, this will be a long one. Guys, if you like my videos, if you like my videos, if you like what you see, give me a thumbs up, like my video. Please subscribe to my channel and ring the bell. So press the bell button to be informed, notified when I have new videos. I have to ask again to just do these things because in the last months I have YouTube is removing a lot of views from my videos and even subscribers without knowing why. Probably the AI that does that thinks that many of the views are from robots or something. But come on, on my channel, in this small mini mini channel with not even 1,000 subscribers, and you see how the views are. It is ridiculous in comparison to other channels. It's so low. And even there, for my previous video, they deleted, I think, 10 views for I don't know why, and 2 subscribers. I would understand that for big channels, yeah, okay, and suddenly thousands of views came, etc. But for me, were 1 and 2 and 3 and 10 views. Anyway, guys, I would be grateful if you could help me with subscribing and liking my videos. Anyway, let's go to the next one. The next one is this one. It's a DC link capacitor. I hate that. Okay, now it zoomed. That I showed before. This is starting to be very, very bad, very hurtful if it is charged at you in your body. 40 microfarad, 900 volts, potentially lethal. Yeah. So let's check the ESR, but just first let's check the datasheet. Here I have the datasheet. It's from Vishay Rodenstein. Yeah. And let's go down. No, it's the wrong one. Sorry. It's a DC link capacitor. This one, the version without the C at the end. It should be the ESR for a 10 kilohertz, more or less. Doesn't say here, but it says 3. What is 3? Do I have it here? Nope. Anyway, ESR of more or less 5 milliohms. This is what the datasheet says. Okay, we believe it. Let's test it. I wanted to make a short video, but this one is getting longer and longer. Okay, let's go to the capacitance setting at 10 kilohertz, and ESR, and let's connect here. So, what we see here? We see at 10 kilohertz that the ESR is less than 10 milliohms, and we have a capacitance of almost 39 microfarads. Of course, again, completely frequency dependent. Let's go down to see at 10 kilohertz, it's 8 milliohms. So now we have again this thing of discharging, charging, etc. Let's try it again. I just discharged it. What do we say here? Hey, come on, stay connected. 7 milliohms. So, and now we will go to 100 kilohertz. 5 milliohms. And we are exactly at 5 milliohms because at the here, and it is for 4 pins, it's 5 milliohms. I'm measuring, we have to see at 2 pins, it's 6 milliohms. We are very near. But this Note 3 said ESR between 10 and 100 kilohertz. So this is what we have here. 4 milliohms is a dead short, yeah, at this frequency. Now, to compare this one, let's go back, with electrolytics, I have this beautiful Nippon Chemicon KMX series low ESR 100 microfarads at 400 volts. That means we have to put 2 of those in series, and we are not even reaching the 900 volts. We are reaching only, am I correct? Yeah, I'm reaching only 800 volts. So for this KMX series, I have the data sheet, and they even provide a maximum impedance at 100 kilohertz. Look, I have to zoom, it's better. And somewhere here, where with 100 kilohertz, sorry, we should have 63 milliohms at 100 kilohertz. Let's check it. Negative to negative, positive to positive. And what we see here, it's even better. Interesting. Why is this so low? I will discharge it. Again, let's try again. It is how it is. It's even better than the datasheet says, yeah? Okay, this was the maximum impedance. Haha. I should read better. Maximum impedance. So we are full in the ballpark. It's 150 milliohms, yeah? Again, this two of those in series is 0.3 compared, so 300 milliohms compared to the 8 or 7 milliohms of this beautiful capacitor, sorry. Even these beautiful, high quality Nippon Chemicon, original Nippon Chemicon capacitors. Many. But now, the last one. Big Bertha, 200 microfarads at 1 kilovolt. Da, 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 da. Da-da-da-da-da-da. So, I think this was the music of the science fiction series Space 1999. I loved it as a child. So, anyway, this is the datasheet. Here you have high density type KNG 1914, and the 200 microfarads should be at 1.8 milliohms. Ooh, sorry. At 10 kilohertz, tested at 10 kilohertz, 1.8 milliohms. Let's see. Kilohertz, and we have one connection and a second connection, and I have 12 milliohms. That's too much. That's too much. Again, let's discharge and see. Okay, everything discharged. Let's do it again. 12 milliohms. And what happens if I go to 100 kilohertz? There we have the 1 ohm, but I don't know where they stated 10 kilohertz. Anyway, you see the ridiculous low ESR of this capacitor. 1 milliohm. Guys, a sense resistor is even higher than that with milliohms. If you use a sense resistor, 5-watt burn sense resistor for, I don't know, a few milliohms to measure a lot of current, this has more resistance than this one at 100 kilohertz. Deadly bad boy. Yeah, but now, how we compare that with in means of electrolytics. Okay, Here I have two beautiful Kendale capacitors, low ESR, beautiful caps, high quality caps. I use them in switch mode power supplies a lot. 470 microfarads at 450 volt. In series, we have 220 something and 900 volts. That means near comparable to this one. So I will take only one, but I will show you now first the data sheet, because for these ones they even specify at 10 kilohertz. At 10 kilohertz here, and we are 125 milliohms at 10 kilohertz. Yep. So let's go back to 10 kilohertz. This reminds me of the old mobiles when you had to press a button multiple times to get the right character when you send an SMS. Fortunately, these times are gone. Yeah. So we have now. Let's check what we want to check. Yeah. Let's check the capacitance first. So, okay, let's connect it. Minus. Let's discharge it. Minus. Plus. And what we have here, nothing at 10 kilohertz. It cannot measure it. Let's get at 100 hertz. Now we have the 470. You see, these capacitors are not meant to be at these frequencies. The highest frequency is 1 kilohertz, that at least with this LCR meter I can test. If I go to 10 kilohertz, it shows me an overflow. Anyway, but we still can measure the ESR. For that we are going to the resistance mode. And we have 142 milliohms compared to the 125 given here. And this is the typical, so we are totally in the ballpark. Again, you have to put at least two of these in series, then you will have almost 300 milliohms, compared to ridiculous up down to 1 milliohm using this one. So, and now I'm going to stop because it is already too long. The video is already too long, and probably most of you have already switched away, unfortunately. Again, guys, please subscribe to my videos, subscribe to my channel, like my videos. Thank you for watching. See you next time. Cheers.